Welcome to Physical Science. Today we're going to discuss the periodic table, which is chapter 5. First, we're going to look at the history of the periodic table. Our objectives are to compare the organization of Mendeleev's periodic table to the modern periodic table. So we'll look at how the elements are organized, how they were originally organized, and then what changes we've made. We will also define group and period in the modern periodic table. We're going to relate the organization of the periodic table to the arrangements of electrons. We'll introduce that in section 5.1 and then get in more detail in sections 5.2 and 5.3. Back in the late 1800s, scientists had discovered atomic mass, and they knew the atomic mass of all the elements they had seen. Then they noticed that there were properties that followed certain patterns. So they made graphs where they listed the elements in order of increasing atomic mass, and they graphed what the boiling points were like and what the melting points were like, the densities. They also did atomic volume, the size of the atoms, and they noticed that there were patterns. In 1870, Lothar Meyer made a graph. He listed the elements in order of increasing atomic mass. So he started with lithium, which has the lowest atomic mass, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, and sodium. So he listed them in order of increasing atomic mass. Scientists would expect the atomic volume to increase steadily, but then he saw this interesting pattern. It didn't quite work that way. First of all, when you look at lithium, lithium has atomic mass 7, and it has a specific volume. When you go to beryllium, beryllium has atomic mass of 9, but its atomic volume is less. And then when you look at boron and carbon, they have more and more atomic mass, but their volume decreases. Then he noticed that sodium had, once again, a higher atomic volume. Well, it had more mass, and so we'd expect it to have more atomic volume. Then magnesium, which had more atomic mass, had less volume, and aluminum had less volume. And then potassium had more. He's listing the elements in order of increasing atomic mass, and potassium has much more atomic volume. Then as the elements are listed in order of increasing atomic mass, the volume decreases again until it spikes with rubidium, then the atomic volume decreases again, and then it spikes with cesium. So he noticed that as the elements were listed in order of increasing atomic mass, their atomic volume followed this pattern, where it would have peaks on certain elements. Many scientists were creating periodic tables that listed the elements in order of increasing atomic mass, and they looked for ways to put the elements that were similar to each other in similar locations. Dmitri Mendeleev, he made the periodic table that was the most famous. In 1869, the way he structured it, notice that he has listed hydrogen, which has atomic mass 1, then lithium, which is atomic mass 7, and the beryllium, which is 9.4, then the atomic mass increases to 11 and 12 and 14, 16, 19, and then he starts the next horizontal row called a period, and the atomic mass is 23, 24, 27.4, 28, 31. So he's listing the elements in order of increasing atomic mass. That's what we call a period. Then the vertical column, notice what he put in the same vertical column. In group number 1, he put hydrogen, lithium, sodium, potassium, rubidium, and cesium. They all were in the same group because, for example, they all had the peaks in the graph for molar or atomic volume. So he followed this pattern and put elements that were similar to each other in the same group. To summarize, Mendeleev's periodic table, he listed the elements in order of increasing atomic mass. His evidence was patterns in the graphs of physical and chemical properties, and he grouped elements with similar properties. But his periodic table was unique because he left empty spaces for missing elements, and he correctly predicted their properties. He also switched the order of tellurium and iodine to keep the elements with similar chemical properties in the same column. So let's look at this. In his periodic table, he left empty spots, like this spot right here. He said titanium, which has atomic mass of 50, it's right after calcium, which is atomic mass 40. You would think that titanium would go under aluminum, but it doesn't have similar properties. He says titanium is more like silicon and carbon. So he says, I'm going to leave an empty spot because I think we have not yet discovered this element. And he did that in many places. where he left empty spots because he said we had not discovered all those elements. The other scientists said, we've discovered every element. And so they thought it was crazy that he would leave empty spots. But he also predicted what those properties would be like. When he predicted the properties, he said, for example, underneath aluminum, there would be this element. And he said it's going to have an atomic mass of approximately 68. In fact, he said, underneath aluminum, there's going to be a substance that has atomic mass of 68. It has a density of 6.0 grams per cubic centimeter. It's going to be a soft gray metal and have a low melting point. The other scientists did not believe him. And then a scientist announced, I've discovered a new element. This new element has atomic mass of 69.7. It has a density of 5.9 grams per cubic centimeter. It's a soft gray metal, and its melting point is 29.8 degrees Celsius, which is low. In fact, our body temperature is 37 degrees Celsius. And so if you put this substance, which he named gallium, if you put this solid in your hand, it would melt. Scientists were in shock that Mendeleev had predicted the properties of this element, and then it was discovered. So Mendeleev, his periodic table was fascinating because it was unique because he left empty spaces for missing properties, and he correctly for missing elements, and he correctly predicted their properties. Let's also look at what he did with iodine. When you look at his graph, iodine, it looks a little bit like a J, but iodine is in this location. Iodine, it has atomic mass 127. Tellurium had an atomic mass of 128. Notice how these atomic masses increase. Tin is 118, Sb, which is antimony, is 122, tellurium is 128, and then iodine is 127. Iodine has a lower atomic mass than tellurium. So why did he reverse the order? He told the scientists, iodine behaves like bromine, and it behaves like chlorine and fluorine. And so he said, I think iodine belongs in group 7 with fluorine and chlorine and bromine because they have similar properties. In fact, he says, I think the person who discovered tellurium somehow got the mass wrong. We later found out about neutrons and found out that tellurium had a few extra neutrons, and so that's why its atomic mass was heavier than the others. But you can see Mendeleev's periodic table was very unique. He left empty spaces for missing elements, correctly predicted their properties, and he switched the order of tellurium and iodine to keep iodine with elements that had similar properties. Let's compare Mendeleev's periodic table to the modern periodic table. The modern periodic table is based on increasing atomic number. It lists the elements in order of increasing atomic number, which, as you'll recall, is the number of protons. Back in 1912, Henry Moseley shined X-rays on the elements, and he was able to determine a specific number associated with each element. He didn't know that that was a number of protons because they had not been discovered yet. But what he did is he listed the elements in order of increasing atomic number. So on his periodic table, had increasing atomic number, and for hydrogen it was 1, for helium it's 2, lithium is 3, then beryllium is 4, boron is 5, and you can see how the atomic number is increasing from left to right. Notice that when we get down to what's called period 5 is the 5th row down, and it is located here. When we look at period 5, horizontal row, we see the atomic numbers increase from 37 to 38, 39, 40, 41, 42, up to where we get to tellurium. Te has atomic number 52. Iodine has atomic number 53. Xenon has atomic number 54. Look at this. When we list the elements in order of increasing atomic number, the issue with iodine is remedied. We can see that iodine can still be in the same group as bromine and chlorine and fluorine because we are listing the elements now in the modern periodic table. We list the elements in order of increasing atomic number, the number of protons, not atomic mass, which is the total mass of the atom. So let's look at what this looks like when we graph the properties. A periodic law is when the physical and chemical properties follow a repeated pattern as their atomic number increases. Notice that in this graph, we have atomic number that is on the independent variable, which is different than Mendeleev. He used atomic mass because he didn't know about atomic number yet. And when we graph something like ionization energy, that's the amount of energy it takes to pull off an electron, we see this pattern of peaks and valleys. A periodic function is something like something you do every week. At my house, on Fridays, we go out for dinner. And so it's something that happens repeatedly. Another example of a periodic function would be, for example, the temperature. Notice that the temperature increases till about mid-afternoon, and then it decreases. In the night, it's very cold, and then it increases, and then it decreases. These are examples of periodic law. And so the modern periodic table is based on listing the elements in order of increasing atomic number. We give certain names to vertical columns and horizontal rows. A vertical column of elements in the periodic table is called a group or a family, and elements in the same group have similar chemical properties because they have the same number of valence electrons. And we'll look at that specifically as we get into the periodic table. A period is a horizontal row of elements in the periodic table, and the period represents the number of energy levels. Do you remember when we drew the energy shells, the energy levels? That's what a period represents. So let's look at a periodic table and identify the group and the period. When we look at this periodic table, the groups are vertical columns. So for example, group number 1 is located here. It includes hydrogen and lithium and sodium and potassium and rubidium and cesium and francium. These elements have similar chemical properties. And so they're all listed in group number 1. Then group number 2 includes beryllium, magnesium, calcium, strontium, barium, and radium. So these are groups. Groups are vertical columns that list elements with similar chemical properties. The horizontal rows are called periods. So the first period would be the one that includes hydrogen. Hydrogen and helium are in the same period. Then the second period includes lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So you can see that periods are horizontal rows. Now that we've looked, the groups are vertical columns in the periodic table. They have similar properties because they have the same number of valence electrons. Periods are horizontal rows. Let's predict, or let's identify, what is the group and the period of a specific element. First, let's look at sodium. Sodium is located right here. If we want to know which group is it in, group is a vertical column. It is in group number 1. Notice that we have group number 1 that's vertical. What's the highest group number? It goes all the way up to 18, and that's where helium is. Sodium is in group 1. And then which period? Which horizontal row is it in? When we look at the horizontal row, we count down 1, 2, 3 rows. So sodium is in group 1, period 3. Now let's compare it to magnesium. Magnesium. Which group is magnesium in? It's the second one over, from left to right, and so magnesium is in group 2. Which period is it in? It is in period 3 because it's the third row down. And now let's try aluminum. Aluminum is in which group number? Group is a vertical column. Notice that we have 18 groups, and so when we count it over, aluminum is in the 13th vertical column. So aluminum is in group 13. Which period is it in? Horizontal row? Is it period 1 or 2 or 3? It's the third row down, so aluminum is in period 3. This means that sodium, magnesium, and aluminum, what do they have in common? They're all in period 3, the third horizontal row. And what do they have that's different? Sodium's in group 1, magnesium is in group 2, and aluminum is in group 13 because it's the 13 row over. We have completed section 5.1 in which we discussed the organizing of the elements. We have compared the organization of Mendeleev's periodic table to the modern periodic table. We've defined group and period in the modern periodic table, and we've related the organization of the periodic table to the arrangement of the electrons.